Hello, everyone. Can you hear me? Guys, can you hear me? Can you guys hear me? Hello, can you hear me?
Yes, I can.
Okay, great. All right. So welcome to ITS 454. Okay, so today we're going to cover a new topic. So if you remember, I talked about this last week. Okay, so last week we were talking about so let's see. So we did the exam. I graded the exam. So please look on Blackboard. If you have any questions about the exam, you can email me. Then we did the risk assessment video. So hopefully you guys have seen this video now and are all working on the project. So this is project A. Then last week we covered VPNs. And so I gave a lecture on VPNs last week. And then we started the lab on VPN. Okay, so today I need to do a new lecture on anomaly detection systems. So I'm going to do a new lecture on anomaly detection systems. And that's really because this is for the project B, you have two options. Either you're going to enhance the VPN lab or you're going to do this network IDS topic. So one of the two. Okay, so today I'm going to talk about this. I'm not going to do a lab on, we're not going to do a lab on anomaly detection. So basically I'll do the lecture today. This will be on the exam as a question. And if you're interested in this topic, you can do anomaly detection as your term project, okay? So either this one, as I said, or the enhancement of the VPNs. So after the lecture today, please make sure to talk with your teammates, your groups of 3, and decide which topic you want to pursue. And then please email me just to confirm if you're going to do VPNs or IDS, okay? So please send me that information as soon as possible so that I know that everyone's working on it. So just one email per group, okay? And then on Thursday, we're going to continue with our VPN lab. So we're going to continue with this lab. And then next week, we will go over the TLS and VPN topic and finish out the lab, hopefully around this time. I'll have some special topic on the 21st just to cover a few last things, and then you can work on your project on the 23rd. And then finally, your presentations are going to be the week of April 28th to the 30th. So remember, you'll present, project A and project B on both these days. And then finally, we'll have our final exam online. Okay, so before I get started with today's topic, which is network IDSs and anomaly detection systems, are there any questions about anything before I continue?
No, not right now.
Yes,
Oh,
Professor.
Somebody has a
What do you mean by like VPN enhancement? So you said that we would choose either between the IDS or the VPN, right?
Yes.
Okay. What do you exactly mean by like enhancing the VPN lab?
So with the so I gave this example. So the VPN lab is basically all done in VMs, right?
Correct.
It's all VMs, really. You need 3 VMs, and then you got the code. Hopefully, you started working on it. But what I had said, given that we have this very particular situation where all of you are at home, and if you're in a group of 3, all your friends are at their homes, right? So you have 3 houses. So you could try to implement that same code that you use on the VMs, but actually expand it to include your physical hardware at home. So for instance, create a VPN between your, Trevor's house and Evan's house, Evan Bray.
Okay.
You know what I mean?
Yep. So I remember you saying that. So that would just be what you mean. We would just basically create our own and connect to each other's, you're saying?
Yeah, pretty much. So as you know, you're going to put the routing rules on the VMs, but in this project, you would have to be, one crucial aspect is you need to be able to get into your home router.
Yes.
You need to be able to put in a couple of routing rules there, and your friend at his home needs to put in some routing rules. And that way, I mean, I know it's a challenge, but I just think, hey, that would be a nice thing to do. It's a nice
Okay. Well, how about if we were just to start doing that from the beginning and not do the VMs, would that work too or no?
As far as, but the thing is, so you're confident, so as long as you do it, it'll count towards the lab, yes, because you're doing the lab plus also enhancing it.
Okay, so if we were to accomplish that, it would count for both the lab and
Yes,
the project.
I'm totally fine with that.
Perfect.
The downside of that is if you're unsuccessful completely with the physical setup, then you didn't do it for the VMs either.
Correct. Okay.
Yeah, that's it. But I mean, I know you guys sometimes like a challenge, and so I'm giving you this opportunity, right? So for everyone else, we're just going to do it in VMs, and we'll talk. We have a couple more weeks to work on it. But for those of you that like to physically implement so here's the scenario that I would say, and I'm not saying that you should do this, but this is just a made-up scenario. Imagine that, let's say, Trevor, right? So you have your router and you get your Netflix and everything, or have some, or how cable, if you have cable TV, it's somehow regulated by the router. You know what I mean?
Correct. Yeah.
Right. So then Evan doesn't have cable. Let's say your cable.
Mm-hmm.
Somehow, by VPNing into your network, now Evan can see cable. Does that make sense?
Yeah, it's just because it's specific.
Because he's in your network now, right? So everyone in your network would have access to HBO, but if you're not in your network, you don't have access to HBO.
Okay.
So something like that. I mean, to me, that's a nice little project. You had a goal to achieve, and you did it. So,
perfect.
Yeah. So keep in mind though that we still haven't done the crypto part. Now most of the code is provided, but this is a very much, well, actually both of these assignments, now that I think of it, have code involved. So I think it's a nice challenge, but I want to give everyone the option. So you select which one you find more interesting.
Okay. Thank you.
I have a question.
All right. No more questions?
I have a question.
Yeah, go ahead, please.
Okay. So we're wanting to do this VPN with this C lab or the C code and everything like that and get it encrypted and all that sort of stuff. I'm used to using VPNs to where you do like a PPTP that's already set up and you just enter your information and
you mean like an open VPN on Linux?
Well, yeah, OpenVPN, whatever program that you've already got that will run.
Well, OpenVPN in Linux, yes.
Or I mean, to me, the ones that I like better are the IPsec style, to where it's site to site. There's no login needed. It's like the network's connected. It's just you put it back in on the hardware.
What are you connecting to? Do you mean like you're connecting to a website? You mean?
No. I'm saying site to site, point to point, like house to house. You're talking about.
Right. Okay. So physically, you would have it. So are you saying you have a VPN device at home? I mean, what would be your VPN server?
Well, technically, yes, I have a VPN device, but I mean, a lot of these routers that everybody's got in their houses, they've got VPN capabilities for the login style VPN.
So who would you connect to?
I could connect with my teammates.
Okay, so your teammates also has a router that has built-in VPN functionality. That's what you mean?
Yeah. Yeah, whether we do it like a virtual machine with a VPN.
But you still need to do the lab though. That, you can
okay.
do the project like that. we might need to add a little bit more difficulty to it, but it sounds plausible, yes.
I'm not in the mood for difficulty. My difficulty went out at the first 5 weeks of the semester, if you remember that.
Okay. So, I mean, you could add like Active Directory. You could add an Active Directory server or something like that. I do think that the one where you implement it in code is a little bit more difficult than the one that where you, because that, you know, you don't really have routing rules or anything if you're doing it from site to site, my device to someone else's device. You know what I mean?
True.
I just think it's a little bit easier. So we can talk about it, but I certainly, it's a project, right? So the project is open-ended. It's just, let's make it interesting is all I'm saying. I mean, now, you know, nowadays you can just get like, I forget, there's online, there's something called VULTR, Vultr.com. I mean, that's a VPN too, but it's, you know, pretty straightforward. You know what I mean?
I'm not familiar with them, but okay.
No, right. But I'm just saying, so what I'm saying is there's several levels of how to implement this, and some are so easy that, you know, not sure that's a project type of a thing. But your idea sounds okay.
For the IDS idea, is that
another question? Is that still Daniel?
that's a separate question. For the
Okay,
IDS,
another question?
basically you develop and set up your own IDS. Is that what that's all about?
Right. This one you have to, there is no, for this one, there's no open IDS software, or it's not in your device. You have to implement some code.
So no utilizing Snort or such like.
Yeah, it's not us, because Snort, see, here's the thing, and this you're actually now getting into today's lecture. Snort is a signature-based IDS. But not everything is a signature day attack. You know what I mean? So right now we're going to talk about the types of network attacks that are called zero-day attacks. So zero-day attacks don't have
Signatures.
been seen before, right? So there's no signature for them.
So if we did like a 30-day trial with somebody like ProtectWise, oh, I'm sorry, the Verizon now, and did a project on that, would that be along those lines?
On what? Sorry, I'm sorry. On what?
Doing a 30-day trial with somebody like who's now Verizon, used to be called
30-day trial of what, Daniel? You're
ProtectWise IDS.
And what does that device do?
It's a complete IDS. It takes everything that goes through your network and uploads it to their sandbox. And if there's
so they do the analysis for you. You're not doing it.
Yeah, they use Snort style.
Right, but that's right. But so the whole point of this is that you're gonna implement something. So look at the video first, right? You know, it's not as difficult as you might think, and decide after. Decide if you want to do. Like I said, you don't have to do it. It's a choice, but it has to be, as there has to be some difficulty. There's got to be something that you're implementing that, you know, that works at the end of the day. Do you have any other questions?
No, thank you.
Okay. All right, guys, are there any other questions? All right, no other questions, so let's get started then. Okay, so as I said, today we are going to focus on this lecture. This will be on the exam, so pay attention. And then if you want to choose this topic, this is more of the advanced topics. I already kind of hinted at it because of Daniel's questions. And more systems, you know, have to have these functionalities for your network analysis. Okay, and then on Thursday, we will continue with the VPN lab. So I have a question. Has anyone made progress on the VPN lab? Have you guys at least started?
I'd gotten started on it, and I had run into some issues that I haven't yet resolved.
Okay.
I can't remember what they are at the moment. But,
anyone else? Guys, anyone else?
Susanna, who's part of my team, she started with something, but then she ran into an error that she still hasn't been able to solve. And I personally haven't started my own take on the lab as of yet. That's my plan for tomorrow, is to focus on doing that like all day tomorrow.
Okay. Shashing, have you started working on the lab? Wen Liang? Okay.
Yes, we are starting working on the VPN stuff.
Okay, so you started working on it. Okay. Paulo,
Yeah.
guys, Neil, have you guys started working on it? Trevor?
The basics of it. We haven't gotten very far with it yet.
Okay,
but-
so it seems like you're all, so from what I gather, you're all kind of just getting into it right now. Okay, all right, that sounds good. So like I said, we'll spend a couple of weeks on it, and then today, let's get started with anomaly detection. Somebody wrote something. Okay, good. All right, so some people are making progress with it. Sounds good. All right. Yeah, you just use the code that's provided. So nothing, there's no need to write from anything from scratch, maybe modify the code. Okay, all right. So anyway, so we are here on April 7th. Okay, so if you look on April 7th, I've already I have, obviously I'm recording this video and I'll post a link here. And I'll see if I provide some code to help you guys out, but I really want to see what you can do. You can write the code in Python. Now, I have provided some help, okay? So basically, this is going to be, so we talked about firewalls in the network, right? And then we talked about IDSs like Snort. But the problem with all of those is that they can only address known attacks. So now we need to look at other ways of dealing with issues in the network, which we're going to define as anomalies. So we're not even going to go as far as saying, oh, we're going to create a zero-day attack IDS. Instead, we're going to just look at anomaly detection because it's an easier problem to look at, okay? So that's what I want you to get out of it. All right, so a couple of things I want you to do for this lecture. I want you to read this paper. So this paper, I provided a link. You can download the PDF and just read through it, okay? Make sure you read through all the details. This paper will explain how to use this tool, CyberSecTK. So CyberSecTK is a Python library, okay? Using the SCAPI library, the SCAPI network analysis library. So the way it works is that CyberSecTK is meant to be a tool that, as you know, the network data is basically, packets, right? So we can use Wireshark, TCP dump, one of those to collect data. So in this, for those of you that do this project, you will need to collect network data, and you can do that with Wireshark, etc. That will create some PCAP files, right? So PCAP files. And then those PCAP files are going to be the input for CyberSecTK. Then CyberSecTK will convert those packets into a representation called the feature vectors, and those are the input that we will feed into our anomaly detection algorithm, okay? So that's basically why I've provided these. So this is one of the libraries you can use for this. You can use Wireshark to collect the data as PCAP files, then use this tool to extract the data from the PCAP files and create the data that you feed into your anomaly detection system. Additionally, you can read this paper for further information. I also provided this link to this tool, Weka. It's a very nice GUI-based tool that allows you to visualize information, okay? So those links are, I recommend that you read through them, right? There might be also some questions about the paper on the exam. All right, now that I've talked about the links, let's go, let me close this. And now let me go to, I need to screen share. I'm gonna go to the slides here. Okay, all right. So as Daniel indicated, right? So he knows about intrusion detection systems. Intrusion detection systems, IDS, right? And all of this is, of course, for the network. Can you guys, by the way, can you see my slide I'm writing on?
Yes.
Like a whiteboard, okay, great. So one of the downsides of IDS is, so they have, there's advantages and disadvantages with standard IDSs, right? So let me put it this way. Let's look at Snort. So what is an advantage, or what are advantages and what are disadvantages of Snort? What would you say? What are advantages and disadvantages? Anyone? Guys? Okay, so you're writing. Let's see. Open source, sure. What else? One more. Come on, let's see if you guess. Yeah, they handle signatures. So actually that kind of relates to that. So an advantage of Snort is that because it uses signatures, right? What would you say about the precision of Snort when it finds an attack? Would you say it's high or would you say it's low? Okay. Right, it's high. Thanks, Alicia. So it is high, it's high precision. That's very good. So that means that whenever it finds something, it does really well because it has a signature for that particular attack. On the other end of that, the disadvantage is if it has never seen an attack before, because it is what is called a 0-day attack. So those are attacks that are really, really new. Okay, so if it's a 0-day attack, what's the precision like for that? Zero, right? So exactly, it's never seen it. That's a good answer. 0, it won't detect it. Very good. So exactly, it's not going to detect it because so the precision is going to be very low. Okay, so it doesn't know 0-day attacks. However, 0-day attacks do occur. Okay, they do happen. Okay, and so how, the question that we want to address here is how do we deal with this kind of a situation? Okay, so there's all right, so there's basically then we want to deal with 0-day attacks. Now, there's basically, let's say there's two main approaches. We could build a system, and the system, we could have in the system, we would spend a year or two collecting data, and we would have two types of data. We would have normal data, and then we would have attack data. So we don't necessarily have all the attack data in the world, and we don't have all the normal data in the world, but we do have some data, all right? So we have some normal data, and then we have some attack data, okay? And so the question is, if we had plenty of both, we could build a system that kind of learns like the normal distribution of normal, the normal distribution of attacks, right? And then whenever we are faced with a new attack, you know, each model would look at it, right? And it would say, oh, this looks like an attack. You see that, guys? Does this make sense?
Yeah, that makes sense.
Okay. The problem with this, though, is that we need this attack data. And you know what the question is, what exactly is meaningful attack data? So right now you learn in the class that you guys can use netwalks, right? And you can spoof packets, and you know how to craft attacks based on snort rules, right? So, you know, so this is kind of one of the questions on your exam was about that, right? Create an IDS system and make sure that the IDS system can detect 3 types of attacks. And I think I said like denial of service and something like that. All right, so the problem with it is that you guys would have to collect this data manually. And, you know, but does that address, you know, will that address all families of attacks? Probably not. I mean, just look at Snort. Snort had like 20 or 30 different families of attacks in there, right? Let's see. Yeah, it won't detect it. Right. And so this is the issue that we're trying to address. Okay. This is actually a very big issue. You know, network data is huge. You know, every organization will be different. That's the other problem. So I want you to understand something. You know, if let's say you wanted to build IDSs for different companies, well, the attacks that you're going to encounter at Bank of America, right, are going to be very different to the attacks that you would encounter at, you know, P&W versus the types of attacks that you would encounter in healthcare. You guys see that? So everything needs to be very specific to the network. And so that, you know, this approach has disadvantages, right? Because, you know, you have to, you would have to find just one common set and then try to generalize this approach to Bank of America, P&W, healthcare. It's just not going to work. You know, imagine then the Pentagon, right? So the Pentagon, you know, everyone will have their issues that are challenging. You see that? And so that's basically the motivation for this topic. So at this time, implementing an IDS system like this one is difficult. Okay, so it's not a straightforward approach. Do you guys see that?
Are you talking about the attacks themselves as being different?
Yeah, sure. The attacks that happen in one organization, you know, they might be similar in some ways, but they're going to be specific to that bank or to that healthcare. Also, their normal traffic will be very different. So remember, this is not just about attacks, but it's also about normal, right? And what is normal at Bank of America, high, you know, transactions, is going to be different from what happens at a university like P&W. You see that? They all have email, but the behavior of the email movement across the network will be different.
So yeah, each of them are going to be tailored individually to their own.
Yes, exactly. You
destination.
touched on a specific keyword there, and that is tailored. That's actually what you want. You want to tailor a system to the Pentagon, Bank of America, P&W, or healthcare. Do you see that?
But technically, they could all be the same style of attack.
Yeah, but it's not going to work. If you try to build something that's pretty generic, let's say, and then you try to apply it to each company, it's not, let me put it this way, it's not going to do as well as something that is tailored to that type of an organization.
Okay, I get that. Yeah.
You get that, right? Okay. So that's what I'm, well, but see, Daniel, the problem is your generic thing might have an accuracy of 50%, whereas the tailored thing might have an accuracy of 85%. You see that? So although it seems like a semantic thing, it's significant. Do you understand?
You mean trying to be like semantic and being for everyone?
No, I didn't mean semantic. I just mean the semantics of what I said.
Okay. Okay. Yeah.
Okay. So the point is that an IDS system, because you need to have information about normal traffic and information about attack traffic, and first of all, where do you get this? So I ask you, so let me put it this way. So let's see, so you were asking some questions. So let's go back to you. All right, so you want to build an IDS with both types of information, normal and attack data, right? And I tell you that for this to do well, I need to have 1 million examples of normal and 1 million examples of attack. If you have 1 million examples of normal and 100 examples of attack, it's not going to work very well. You see that? Daniel.
Kind of like running it through the thing in 581, the machine learning.
Yeah, but don't bring that up because
Okay, sorry.
don't know that. Okay, so but you know what I mean, right? It's not gonna do well, right?
Yes.
I forgot. This is why you've been asking all these questions. Is that you have a clue of this? Okay, so yes. So you see that there's a challenge there, right? So I want you to have 1 million of normal and 1 million of attack. How do you get me 1 million examples of relevant attacks?
You have to get it from somewhere else, unless you know you're constantly.
Okay, you're going to get it from somewhere else, but this is for Bank of America. Where are you going to get it from?
Oh, they'll have all kinds of data from where they've been attacked.
Okay, they have. Okay, so you're exactly saying the things that I've been telling you. They have data that has been sent to them. You see that? But if you do a machine that from Bank of America data and then try to apply it to the Pentagon, it's a different domain. You understand?
Yeah, they might say that's only 1% of what we've been hit with.
Right, because we have other types of attacks that we've received that are relevant to the Pentagon and not to Bank of America. Nathan saw you could generate artificial attack data based on the network you're considering. Okay, good answer. So Nathan, so how do you do that? You have to
Hire pen testers.
Sure, and then you're going to use NetWalks and some other tool, whatever, and just generate attack data, right? That's.
I figure a little bit, get a red team to go at you.
And they're going to rent, so you're going to pay a lot of money to hire a team to attack your network. First of all, you don't want to attack your network because it's going to disrupt it, right? So you probably want to do this in a simulated environment. I mean, it's not like, Daniel, you're going to be working and you're going to be happy when somebody attacks your computer, right?
Good point.
Good point. Yeah. So, but I see what but that's good. We're getting into the discussion of this, right? So good suggestion, Nathan. Generate fake data, spend a couple of $100,000, hire a team, have them attack your employees, generate the data. Maybe we do get to 1 million of normal and 1 million of attack, right? Guys? Now, so the normal data is certainly the real data because that's just going to be the daily operations. People are working. Then you hire pen testers to do this kind of work, and you're still going to have way more normal data than attack data, right? You would agree with that? Sounds reasonable?
Yes.
Okay. And then now, even if you hire the really greatest pen testers or whatever that work in a lot for banking, when they go to healthcare, do you think they're going to be as effective, or to the Pentagon? And they not just because they're really good doesn't mean that they know all 0-day attacks. Would you agree with that?
Definitely. There's always developing new ones.
Exactly. So you guys see the problems with this, right? So this approach is definitely the desirable one. I'm not saying that it's not desirable, but it's an endless game. It's an endless game that Daniel, as the CEO, decided he was going to spend $300,000 on a red team every year, and now it's been 5 years. He spent $1 million, and the system is not doing that great still. You see my point where this is going, guys?
Yeah.
Yeah, so would you,
Yeah.
Yeah, go ahead. Go ahead, please. Who's that?
so would you have to just monitor your network and see what's normal and what's behaving not in a normal way? And that's how you would, you know, kind of, I don't know, just gather that information and see if that's an attack somehow?
Yeah, can you repeat that? You cut out a little, Susanna.
Okay. So like if you have someone like IT that's monitoring your that's going to monitor your network, and you see something that's abnormal,
Yes.
then is that how you gather?
Right. That's where I'm going.
Attack?
You know, that's where I'm going with this. So I'm not saying that this IDS solution is not the most desirable. It is. You know, I've spent years, you know, trying to, you know, figure this out. I mean, it's not. It's because. And Daniel actually brought up a very interesting point, is the resources. This is constrained by the amount of resources. Okay, I can imagine, you know, the Pentagon could facilitate several million, hire even more red teams from all over. And that would ensure basically that they have the best data, but of anyone else, but it costs them a lot of money. You see that?
Yeah, that's something that a company would want to do anyway.
Sorry,
I mean,
say that again?
I don't think it's something that a company would want to do. Just spend money trying to, you know, well,
Try to generate attacks, right? It's
Yeah.
exactly right. You know, who's going to hire a team? Yeah, I get the pen testing to meet some compliance, but just to generate attack data in our network, I mean, it consumes a lot of resources, and at the end of the day, it may not even do that great anyway.
Mm-hmm.
You see that's where I'm going with this.
Okay, I see your point now.
Okay, and then so I have, let's see. Could you generate, you continuously would have to spend for any new attacks? Yeah, so yeah, exactly. So the problem with this is the resources. And so another thing I want to say is, you know how they're always saying that you guys are always on Facebook and everything, and then they take your data and Facebook sells it because your data has value? Guys? So that's the same here. This data translates into money, right? So it becomes expensive, right? So to build this algorithm, it is very expensive. Okay? So anyway, so I think I've motivated this enough, right? And so what I want to say now is that there's another approach. There's another approach that I could argue could be good. I'm not saying it, you know, this is probably what you would want, but it's so expensive because of you getting that data. It's not practical. Susanna actually summarized it really well. Well, what about just looking at this from another point of view? And so that brings us to the topic of anomaly detection. Okay, guys?
Mm-hmm.
And that's basically what we're going to study today, right? Okay, very good. So now, let's move on to the next slide. Now we're going to look at, we're still trying to build an IDS of some kind. But now we want to explore how we can, basically we want to simplify what we talked about in the previous slide, right? So of the two types of data, normal data and attack data, which one would you have more of?
Normal.
Normal, very good. Of the two types of data now, could you give me a cost estimate to generate the data? Let's say the normal data, how much would it cost you to collect that data?
As long as you have something like Wireshark, It shouldn't cost you so much.
But excellent, excellent. So it's $0, right? $0. Whereas this data, Daniel, you know, he said, no, I'm going to hire a red team and, you know, pay them $200,000 a year, you know, several years. Well, I said, you know, anyone, right? And you can see then the problem is, you know, too much cost. So as a company, well, you're going to say, hey, let's go with the 0-1 and let's see what happens. You see that? And so that's the key thing, because as Susanna said, the normal data is plentiful. We have lots of data. You see that? And so that's what I want you to understand, is that the only limit in these algorithms, the anomaly detection algorithms for network intrusions, the only limit is really the computers that you need to store the data and the computers that you need to collect the data. Okay, that's it. And then after that, so that's a few thousand. I mean, you can invest in that. Sometimes you have servers that are not busy all the time, can be repurposed for that when they're not busy. You know, and so that's how it works, right? So, you know, let's go back to our network over here, our physical network, right? So if we had our physical network, and then you have a server, let's imagine you have a server that collects all that anomaly data, where would you connect it? And how would you connect it? So you know how to do this, right? How would you connect the server to collect the data? And where would you put it? Guys? Can you guys hear me? So
Inside your network, right?
yeah, I mean, you can actually have it in multiple locations, right? How do you connect? What do you connect here? What's the name of the device that we connect here?
Tap.
A tap, right? So we connect the tap, and then the tap then, you know, is connected to this, and then we have some kind of a TCP dump, Wireshark, or Sniffx, you know, some kind of code, and now we're collecting our data. You see that? Now, all we're doing, you know, usually no one's going to be attacking the network, right? So it's just going to be our regular network traffic. Does that make sense? So your emails, your browsing. Now there's encrypted data. And remember that with encrypted data, there's no way. So by definition, if you guys remember from 350, right? Shannon said that if you have a good encryption algorithm, the data that's encrypted is basically random, right? Do you guys remember that?
Yeah.
Yeah. So, you know, obviously if you find a pattern, you have a bad algorithm. So when you have data that's random, then there's no pattern there. So nothing, you know, it's random data basically, right? So it's noise. So that's not going to help you. But so here we're assuming that nothing is encrypted, you know, or some of the traffic that you're looking at, or you're just not looking at the payload traffic, right? You're looking at the other headers, etc. Now, there might be some positions where you can actually collect even the non-encrypted data as long as privacy is respected, right? And even actually, I should say, with these methods, because they're fully automated, they can actually waive the whole privacy thing because no human is reading the data, right? It's only a computer. So anyway, in our scenario then, now we have the anomaly detection system that is collecting the PCAP data. And just remember that this PCAP data is all just normal traffic. You guys see that? Guys?
Yes.
Does this make sense? All right. So very good.
Yes.
Yeah, great. Thank you. So given that situation, so I think we now understand, right? So the challenge here is collecting normal data, but that, you know, that's doable. That's not difficult. In fact, for those of you that choose this as a project, what you will do is you will just collect some PCAP files. So you can collect PCAP files of you browsing, sending emails, you know, SSH or Telnet or something, and you will collect some PCAP data. Now, if you have this, let me tell you this that's important. If you have PCAP data in there of email and of multimedia and of Zoom and of Blackboard and of bank transactions and PeopleSoft and all of that, you have a lot of different types of data, right? Now, what you could do without human intervention is based on protocol or source port or destination port, you can make this, let's imagine this is like a barrel of data. You can make this into smaller barrels. You see that? Let's call it bins. So I'm making the really large bin, that's all the PCAP data that I collected here, into smaller little bins. You see that? So let's say this is a bin just for email data. So what I do there is I filter out, you know, when I look at the packets by the headers, okay, this was, you know, some kind of a SMTP data or something like that, or this was some kind of a HTTP data, or this was some kind of a SSH data, and then this one was, you know, something related to multimedia, and so on. Do you get the idea, guys?
Yeah.
Great. So what you're doing there is you're making the problem easier because this one has too much data that's, you know, it's not homogeneous, right? And so you want to basically break this into little bins that are a little bit more homogeneous, okay? And then once you do that, you know, and all of this is done automatically, right? All of this is done automatically. And then at this point, then you can apply your technique, basically, your algorithm. Okay, so this is where we're going to apply our algorithm to do this analysis. And that algorithm is called anomaly detection. It's literally, although the name anomaly detection, you might think of it as related to network intrusions, it's actually just an algorithm called anomaly detection. Okay, so this can work for anything. This could work for, you know, you have car engines, right? And you measure how the cars perform, and then sometimes you get a car that doesn't perform the same, so that would be an anomaly from the normal performance of the car's functions, okay? All right, so the idea is that you collect the data like this. So this maintains, it's fully automatic, so fully automated. It preserves privacy because humans don't really have to read the data. It's all going to be done by the algorithm, right? And, you know, it's basically a way to detect anomalous behavior. So anomalies. And because we broke it into bins, the fact that we broke it into bins means that it's very specific. We could have 20,000 of these. So instead of just having one anomaly detection module, we could have 20,000 anomaly detections. So whenever we get an email packet, we send it to the email anomaly detection system, and we just want to know if that email that we just looked at is more different than the normal distribution of emails in our network. Is that clear, guys? Or let me put it this way. Are there questions about what I just said?
No.
No? Everything clear? All right, that's good. All right, so now that we have the big picture of this, now let's think about how this can be done, right? So you have, you know, your bins for email, and it's, you know, for email, HTTP, SSH, right? So you have that data. Now remember that what's in here is basically packets. Right? So what you have in there is packets. Packets. Okay? packets. What we want to do now is we want to find a way. So what we need now is we need to figure out how, okay? How are we going to take these packets for email or for HTTP or for SSH and extract meaningful data from them that we can later use to model our problem, right? So that's going to be called extracting the features. Okay? Features. Okay? So what I can tell you now is that this step is that cybersec TK that I just showed you. So that toolkit, TK stands for toolkit, it's a Python toolkit, and it's basically made so that it takes PCAP files and then it's going to give you features. Okay, so basically it works like that. You see that? So now you're going to figure out ways of taking the packets. You have bins for email, for HTTP, for SSH, and now we want, given these features, we want to build an anomaly detection system for email, and then we want to build an anomaly detection system for HTTP, and then we want to build an anomaly detection system for SSH. Is this clear? So this is our pipeline, right? And we're going to create 1, 2, 3, N of these, right? And basically now we collect our data. We're going to take any new traffic, run it through these anomaly detection systems, and they will flag anything that they think is very anomalous. Okay?
Okay.
All right, great. So all we have, oops, sorry. Let me, see, let me add some more slides here. All right, so given this, now we just have 2 more problems to solve and we're done. Okay, so we know we have the PCAPs. Now I need to convert these into features. So I need to know how. And then I need to build an anomaly detection system or algorithm, anomaly detection algorithm. And I also need to tell you how. So the great thing about this one, the anomaly detection algorithm is already defined. This one is defined. Okay, that's defined. And so that one, I'm just going to give you the algorithm and then you guys can implement it. Extracting the features will involve using that cybersec TK, but also that will only give you some data. So let me now give you the description of these 2 steps. So first I'm going to describe this one and then I'm going to describe this one. Okay, and please stop me if you have any questions. Let me define this as feature extraction and then this one we'll just say is the defined algorithm for anomaly detection. Okay. All right. So let's talk about feature extraction then. Okay, so what is feature extraction? Any ideas?
The items you're looking for.
The items you're looking for, right? So what do we know? What's our data? What is our data? Packets, right?
Mm-hmm.
What are packets made of?
Headers and data.
Exactly, headers,
Yeah.
right? So there's headers. So what headers do we have? We have a Ethernet header, IP header. If it's an ICMP packet, then it's an ICMP header. If it's a TCP packet, it's a TCP header. If it's a UDP packet, it's a UDP header, right? And for some cases, we also have payload. Would you agree?
Yes.
Perfect. All right, so now tell me pieces of information that you can find. So what I'm gonna do is I'm gonna create a little data set over here, and I'm gonna say packet 1, packet 2, packet 3, packet 4, and so on, right? And we need to up here define some features that they have in common or they don't have in common, right? Please tell me, this is feature 1, feature 2, feature 3, feature 4, feature 5, and so on. So what are some, and remember, we're building bins or anomaly detections for SSH, email, HTTP, what else? Multimedia, and so on, right? So now please give me some suggestions. What's one feature for these packets?
Do we usually look at like the source and destination of
The ports, right? Those were very
ports,
common when you were doing the ACLs, correct?
Right.
Okay, so then we can do source port, destination port. Very good. Do all packets have these?
Yes.
So,
I
like,
think so.
yeah, and UDP
How about Ethernet?
they definitely have it, right? So for instance, let's just say the destination port for packet 1. Let's say packet 1 is SSH packet. What's the destination port?
22.
22. Perfect. You see that? And then packet 2 is an HTTP packet. What's the destination port?
Is that 80?
80.
Exactly. And then packet 3, the destination is telnet.
21.
23, right? That was 23.
23. Sorry, I forgot.
Right? Now, we could also have one, let's say feature 3 is basically, is this an ICMP packet? Do you see that? Let's say packet 4 is a ping packet, but the other packets are not ping packets. Then what would you say for this one? Is P1 an ICMP packet? Only P4 is a ping packet. So is P1 an ICMP packet?
No.
It's
And P2 isn't, and P3 isn't, but P4 is. Do you see? Guys? Does this make sense?
Yes.
Okay, and you can just keep doing that. For instance, let's say that F4, you can define these features to be whatever you want. So let's say F4 is size of data sent. So size of data sent, right? So look at the packets SSH, email, HTTP, and multimedia. Which one of those 4 packets, types of packets, would you say would send the most data?
P2.
Why P2?
HTTP?
HTTP? Daniel?
Say that again.
Why P2?
Because web access and web usage is usually the most used.
The most, right? And if you have, let's say, even a multimedia packet, would you say those could be a lot of data?
They would, but they normally don't travel on 80, do they?
I'm not saying it has to travel on 80. It could be you have a P5 packet, right? And here it's some other value X, but the size of the data is really high, 1 with a lot of zeros. You see that?
Then you would expect that to be like a video of some sort or another video port that uses that.
Sure, exactly. That's what I'm saying is this is how you extract the features to represent It could even happen that maybe, let's just say for the sake of argument, you know, ICMP packet is not associated with a port, right? So you have P6, actually P4 was ICMP, right? So there was actually here no value. You see that? Because it wasn't associated with any kind of a UDP or TCP destination port. Is this clear, guys?
Yeah.
All right, so this is what I'm saying. You have to go from the packets themselves into this to find ways of quantifying, you know, the number of bytes sent, number of bytes received, source port destination, size of payload. Is this an ICMP packet or a TCP or UDP? Does it have payload? Does it not have payload? Is it encrypted? Is it not encrypted? Etc. Lots of options. This could be thousands of things depending on your creativity. Is that clear?
Yes.
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 Okay. The only very, very, very important thing is that whenever you define a feature, let's say F4, size of data sent, they all have to have every packet as you represented. Their fourth column has to be for size of value sent, even if it doesn't relate, right? So even if these were all, you know, really high numbers, you know, all really like really, really high numbers, and then it turns out this one is 0 because it's not even relevant to it. It doesn't matter, but it needs to have it. The fourth column for every single packet in your data needs to be the size of data sent, if that's how you define it. That's about the only requirement there. After that, you can use all the creativity that you want to define the features.
Okay.
All right, that makes sense. So let's just do, so before I move away from this part and start talking about the algorithm, just give me, you know, give me please like three more features. F7 and F8. What would you say they could be? Remember, it's all coming from packets, so just give me some ideas. I just want to make sure that this is 100% clear for everyone. So just give me F5, F6, F7. What would be some additional features that you can have here?
Let's see.
Mm-hmm.
Connection time, maybe?
Connection time. So the time when, is that in the packet?
No, no, you're right. It's not.
Yeah, so just something, so for what you're saying is not wrong. It just means that now you have to look at other things. You know, I mean, you could look at logs and you can look at other things, but I'm trying to keep it just to packets in the network. So just to keep it simple. So just think of packet headers. Oh, somebody wrote something. Oh, Evan Brady. So sequence and ACK numbers, sure. You could look at that. What else?
Isn't in the packet, if it's a retransmission, that's in the packet also?
Okay, so you're saying, so how would you create a feature for that? F5.
Checking like the errors.
Huh?
It'd be like the errors if it's resent packets.
So you basically ask the question, is this a reset packet? You see that?
Not a reset, but a resent. You know, if the packet's not received, then the system sends it again. Is that
Oh,
in the packet?
Sure. Reset, right? Resent. Okay, so then how would you mark that?
Either yes or
One,
no.
correct? So this is a 1, that's a recent packet or not. You see that? Hello?
Yes.
Yes.
Okay, great. Just one more, come on. Someone else, someone that hasn't spoken. Just give me one good feature that's in the packet headers that could be used. Nobody?
Didn't you use like the IPs themselves rather than the ports?
You could. I mean, especially with geolocate, you know how some IPs are tied to geolocation? That could be of use, right? Or yeah, that could be something. What else? How about port, it's not port number, protocol,
Oh, yeah.
right? Protocol, right? So protocol. So I think TCP is 6, I believe. And I don't remember the other ones, but there's numbers for protocols. So that,
You mean like
Yeah, go ahead.
UDP, ICMP, all that sort of stuff?
yeah, exactly. They're associated with, so like UDP and TCP, I'm pretty sure TCP is protocol 6. I don't remember the other ones. You could also look, even though the payload is encrypted, right? You could look at the size of the payload. You see that? Guys, that could be something else, and so on, right? So hopefully that's the idea. So I'm gonna ask you the question, is this clear, how you go from packets to representing them as features? Are there any questions about that?
No.
Oh, it's pretty clear.
Okay, excellent, excellent. All right, so now let's recap. So you're building your anomaly detection system. So you have a PCAP file, break it into bins. These are bins. You have the little bins over here. ... Another bin. They are for specific services or something like that. Then from there, you know, these are packets. Packets. And now you have to extract them into feature vectors, right? So you're going to create the feature vectors. So I'm just going to say features. And that, when I say features, that just relates to what I just described here, right? So that's features. So once that's done, now you're ready to implement your anomaly. Actually, yeah, no, let me do it like that. So now you're ready to implement your anomaly detection algorithm. So I'm just say AD. Okay? So now what we need to do is I'm going to define how to do an anomaly detection algorithm. Detection algorithm. So there's a course that you guys take, and it's called statistics, right? You guys take stats?
Mm-hmm.
Yep. And so you take it so you can do things like this, right? So now you're going to use a little, you're going to see how something so basic that you learn in that class can be used to build this algorithm. So the algorithm's not difficult at all, okay? And please, if you have any doubts, just ask me, okay? And I'll explain it. All right, so basically the idea with anomaly detection is I'm going to simplify this. So I have packet 1, packet 2, packet 3, right? And I have, I'm just gonna have 2 features. Keep it simple. And they are going to be size of payload. We talked about that, right? So the size of the payload. So it turns out that this one has like 2 bytes, and then this one is, you know, I'm just making up numbers. This one's, oops. This one is 10 bytes, and then this one is 20 bytes. Okay. And then over here, what would be another? Someone pick a feature. What's one good feature?
I'd go port or
Port?
Yeah.
The
Yeah.
destination port?
Yeah, sure. Let's use destination point. Okay. And so destination port will be here. For this packet, it's going to be port 80. And then for this packet, it's going to be
22.
Sorry, say that again?
22.
22. Well, I'm trying to, yeah, let me do this. And then this one, the size of payload is 2, is going to be port number 40,000. Now, this is not exactly how the network works. It's just an example. It's an artificial example for me to explain a point, okay? And then this one is going to be port, let's just say port, yeah, 22 is fine, 22, okay? So now what's gonna happen, and these are, so let me erase them. These are going to be X1 and X2, okay? Or feature 1 and feature 2, it doesn't matter. So what I'm gonna do now is I'm gonna plot it. Okay, so this one's X1, this one is X2. Whenever I use, so I should say this is for anyone, any statistician looking at this video. Whenever I use port numbers, like destination port, I am aware that this data could be categorical, and so it should not necessarily, there's no meaning between 22 and 4,000, right? So it's categorical data, and it should be one hot encoded, but I'm only using it for this example. All right. So anyway, so I have X1 and X2. So what I'm gonna do now is I wanna represent each one of these packets in this graph, right? So let's start with the first one. P1, so 2 would be about here, and 40,000, so let's say the scale is like from 65,000, 65,000 to 0, and then from 0 to size of payload could be, let's just say 40 bytes is the limit. You guys see that? Is this making sense, guys?
Yeah.
Okay, so now I'm gonna plot each packet. So the first one, 2 and 40,000, about there, would you agree? That's packet 1.
Mm-hmm.
All right, packet 2, it's gonna be about 10 and 22. So would you argue it's about there?
Yeah.
Roughly? Yeah. And what about packet 3? Packet 3 is, 20 and 80, so it's roughly about there, right? So this is packet 2, packet 3. What do you guys think? You agree?
Yeah.
Okay, that's roughly, right, where they fall. So now imagine that. Now imagine that I put more packets around this one and more packets around that one. Do you see how if I do this, what happens is you could almost see, so if I asked you, given what I just drew here, and you wanted to create 2 clusters of data, what would they be? What would the clusters of data be there?
The ones around P1 and the ones around P3 and P2.
Perfect. Exactly. You see that? You see how that works, guys?
Mm-hmm.
Went from packets to representing them as features to being able to plot them, and now to being able, we can plot everything in this space, we can actually infer things about them, such as calculating that there's 2 clusters in there. You see, that's a very important concept. So that's clear, I'm hoping, okay? All right. So given that, now we're ready for the anomaly detection algorithm. So anomaly detection algorithm. All right, so now I'm gonna forget about, you know, like what I was doing with the packets there, and I'm just going to generalize the model. Okay, so now I generalize the model just as x1, x2, and then I have some data. You see that? I have this data, right? Now, could you, if this was a whole bunch of data, could you tell me where the mean of this data would be located? The mean is like the average, right? Is the mean is now this, we go into your statistics class, right? The mean, right? So where would you put the mean of this data now?
The center X probably.
The center, right? So that and like that, right? So that's your mean. And then if you remember, what was the other term that you had in statistics? That's very important. Mean and?
That was forever ago.
The variance, right? Or the standard deviation?
The standard deviation.
Yeah, okay, great. So let's say the standard deviation or the variance. So what that tells you is how many standard deviations do you have from the mean? So for instance, because this is a circle, this is like in 2 dimensions, we start to draw like that. Do you see that?
Mm-hmm.
So if you look at this in the other way, like if I flip this and I looked at it from like the side, that data would look like this, right? You remember that? What is this called?
Shoot.
So this is called the Gaussian or the normal distribution. Gaussian or normal distribution. The advantage of this is that the whole world pretty much follows this distribution, right? Your data here has a mean, right? It has a mean, which is the center. This is the mean. And then you have standard deviations about like that, right? So now I ask you this question. If I put, I'm going to use, instead of an X, now I'm going to use a square. If I put a new packet and I put it there, what would you say about that packet? Is that packet part of the normal distribution or is it outside of the normal distribution? That is to say, you know, all these packets that are here, if you calculate them, they have a normal distribution, which basically means it's normal, right? It's not an anomaly, it's normal.
Mm-hmm.
They're all around a mean, which we identified as this, and they all have this rule that they're within these 3 standard deviations of that mean. They don't go further out. Most of the packets, roughly, you know, 99% of them fall within that interval. Does that make sense?
Mm-hmm.
Yeah.
So if I put this new packet here, it's kind of equivalent to me putting it there, or maybe even here. So what would you say about that packet?
I would say that that is not anomalous. It's not that.
It's not exactly. Another way of saying it is you would say, I believe that it is part of the normal distribution.
Mm-hmm.
Kyle? And even a better way of saying that is saying, hey, you know what? I believe that the probability that that packet belongs to the normal distribution is good, is high, right?
Yeah.
Exactly. So that's it. I mean, you literally now have the algorithm for anomaly detection. Now I do another one, and I put the packet, let's say, over here. So that's equivalent of this packet being out here, right? There. So what would you say about this one? Would you say the probability that it belongs to the normal distribution is high or low?
Low.
Low, very good. And if the probability, so and here's the trick. Once you say that the probability of it belonging to the normal distribution is low, basically it is a.
It's not. It's an anomaly.
It's an anomaly. It's an anomaly. Perfect. You see that? There you go. It's an anomaly. Does this make sense, guys?
Yeah.
Yes.
And so that is what the algorithm is, right? So now we can look at the algorithm, and I'm just going to give you a little bit of notation so you know how to calculate it, and then that should be it. All right, so please stop me if you have any questions, but basically what we need to define is a model, given what I just explained, that calculates the probability. And you remember we talked about probabilities in 350, and you've talked about probabilities in your statistics class. So we want to find the probability of a new sample belonging to the distribution, okay? Now remember that a new sample, in this case a new packet, will be represented by a vector of features, right? F1, F2. So like in the previous example, we had X1 and X2, right? That's what we had, X1 and X2. So now, you know, I'm going to rewrite these as X1 and X2. They're just some values, whatever they are, doesn't matter. And I have them there. And that's my sample. That's my example. So this 1 and J, I'm going to say it's the subscript J, okay? And if I say a sample, then I'm going to say is XI over there. But I'm not, you know, I'm just going to leave it simple. So the model needs to calculate this probability, okay? Basically, the probability that the sample belongs to the normal distribution, just like I said that before. If it doesn't belong to the normal distribution, it is an anomaly. And the way to do that is, once you calculate probability, you basically have an if statement, right? If P of X is less than some epsilon, and epsilon is some value you have to define kind of by trial and error. So epsilon defined by trial and error. It's experimentation. You have to find a cutoff, basically. But basically, we're going to say if the probability is less than epsilon, then anomaly. Else if the probability of X greater than or equal to epsilon, then packet is okay. Make sense? Questions?
No.
No questions. Very good. All right, so now, so I talked a little bit about the Gaussian, right? So I talked about the Gaussian distribution or normal distribution, okay? And so for that, we need the mean and the variance. Mean and the variance, and that just translates as I drew before. I have a little normal distribution there, got the mean here, and I got the standard deviation. Oops, not the variance, just the standard deviation here, like that. Okay, another way of writing this, it's saying that X is somehow part of the normal distribution given a mean and a variance, right? That's another way of putting it. Make sense?
Yeah.
Okay, great. So now, what do we need? Now, to finish this algorithm, I just need to have the formulas, right? That's all we need. And this is from your statistics class, right? So the formula to calculate the normal distribution of 1x will be as follows. Right, so the formula of 1x is given mu and variance, right? So those are the parameters of that normal distribution. You have to calculate these based on your data, right? But once you have them, the formula is 1, 2 pi square root standard deviation exponential, so this is multiplication, exponential negative x, that's the x minus the mean squared. So that's like the difference between, I have my x here, right? And so x is there, and then I just measure the distance between, right? So that's what that is, and that's divided by 2 variance, and that's it. That's pretty much almost the entire formula, and this is nothing more than the formula for the normal distribution or the Gaussian. You see that? And so that again, the interpretation of this is, you can see that here. Does this x belong to that normal distribution? And so what this gives you here is, you're asking, given this mean and this variance that represents my data, because you calculate it by looking at all these points over here, right? So given that I've calculated all those points, I want to calculate the probability that this x is part of that distribution. Or in essence, you just said, if you say it in opposite, you want to know if this x is an anomaly to that normal distribution, given that equation, which is just a standard Gaussian that you learn in your stats class. Questions?
Nope.
Okay, great. Now all we need is, we need to calculate, because we're using the variance there, we're using the mean there, right? And so we need to calculate those values. Well, let me give you the formula for that. All right, so I'm going to give you, oops, oh, hold on. So now, we're almost done. I'm almost done with I'm pretty sure you get where I'm going with this. So now let's define the parameters, right? So we have the probability there. Now we just need to calculate the mean. The mean is pretty intuitive, right? You take the number of samples, and then what do you do? Guys, what do? You sum them, right? You guys remember this symbol, the sum? You take of I equal 1 all the way to m. So you sum all the values of x, and then you divide them by the total, and that gives you the mean, right? And then the variance is calculated 1 divided by m, I from 1 to m, and then it's just going to be x minus the mean, okay? So for all the samples that you have there, you're going to calculate the difference between each sample and the mean. You square it, because to get rid of the negative, because sometimes you could do like 2 minus 4, and other times you can do 4 minus 2, so 1 is going to be negative, so you get rid of that negative. So I can say this is the sample, and then this is the mean. Okay? So those are just the standard formulas for that, mean and standard deviation. Okay, so that usually works for one sample. The problem is that we now have each packet represented. So we take a packet and we represent it as a vector of F1, F2, F3, ... Fn. You see that? So the formula that I just gave you would work really well if each packet was just F1. You see, because there's only one feature, but we actually have to apply it to every single feature. So for instance, if we have source destination port, right? The destination port could be any number between 0 and 65,000. If we have the number of bytes, it could be any number between 0 and 40 bytes or something. Right, guys? Right. Okay, good. So that's what I need to do. Okay, I need to account for that somehow. How do I, how do I apply these formulas if things look like this? Well, as it turns out, you can still, because you're still calculating the probability, right? So for this one, you calculate the probability, but now you have to calculate what is called a joint probability. So it's basically like saying, you know what? I have to calculate for F1 and then for F2 and then for F3. So you see that? So for every one of the features, I have to calculate a mu1 and a standard deviation 1 for that feature. Then I have to do the same for mu2 and standard deviation 2. And then I have to, generalize to Fn, ... And I'm going to say I need mu(n) and standard deviation n. You guys see that?
Yeah.
Great. So that also translates into saying I have to calculate the probability for F1, the probability for F2, the probability for Fn, and so on, right? But we only know how to calculate the probability. Oops, sorry. We only know how to calculate the probability for 1, which is this one. So we need to figure out how we can do that. Well, as it turns out, there's a rule that says in probability that we can calculate what is called the joint probability. When we have a situation like this, there's one condition for this, and that is that F1 should be independent from F2, and F2 should be independent from F3, and so on. Now, does that hold in packets? Is it possible that when you have destination port that could correlate to packets, size of packets sent? What would you say?
Yeah.
They could correlate, right? Which basically means they're not independent. You guys see that? However, for joint probabilities to work, the features have to be independent. So here, what we do is we make what is called a hard assumption. So we make a hard assumption, oops, of independence. We're going to say that F1, F2, F3, Fn are independent. So we assume the features F1, F2, ... Fn are independent. Even though they may not be. That's why you say you assume. However, once you make that assumption, you can use the technique, then you try it out, and sometimes it works. That's basically what's going on here, is that, you're like, well, I'm not sure about this, but then let's try it, and guess what? It works okay, so that's fine then. Is this clear, guys? Guys? Hello, can you hear me?
Yeah, I can hear you.
Okay, great. So then at this point, we are ready, right? So if we have a sample X made up of X1, X2, the two features such as, source port and bytes, right? So now we can proceed and calculate the probability that it belongs to a normal distribution by calculating the joint probability. So we calculate the joint probability, and that basically translates into the following. We're going to do Px, it's going to be equal to, and X is the vector. Oops, no. Hold on. Okay, so we're going to say that Px is the sample, let's say, and then to calculate the probability that it belongs, so this probability of X belonging to the normal distribution, right, of mu variance of this data, we just do P of feature 1 times P of feature 2 times dot, 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 xn. Do you see that? So that's all we have to do. We calculate the normal distribution for each feature, and then we calculate the probability for each one of the features, and then we multiply. And then that will give us one single value that we can use. And that's going to be our joint probability. So this x1 is going to be feature 1. So we look at the distribution of feature 1. We look at the distribution of feature 2 all the way to the distribution of feature n. So another way of saying that is we have features. So for a given, for X sample made up of F1, F2, F3, we have feature 1, feature 2, feature 3. So we need to basically say if that F, which is X1, X2, X3, we need to say if these belong to their respective distributions. So that's going to be the normal distribution for the X1 data, which will have its own mean, 1, and its own variance for 1. And then for the next feature, X2, that has its own mean for its own data, mu2, variance 2. And then the next one, all the way, let's say instead of 3, let's just say n. And then this is n. And so this is going to be mu n variance n, and so on. Make sense, guys?
Yeah.
Mhm.
All right, so now, so that's really the hard part of this. So now let's just go and summarize this into one formula. Okay, so we just need one formula, which is going to be P, probability of X, of this symbol, which means the multiplication from j equal 1, where j is the feature number, to n features, and we just calculate the probability of xj, right? xj, j, variance j. Okay? So for each feature, we calculate the mean and the variance, and then we just have to calculate the probability that that given value for that feature, xj, belongs. Let me use, I don't want to, let me use this instead. So we're going to calculate, although this says, no, let me not use that. Let me use that. Right, so that's just going to say that this xj, what is the probability that this xj belongs to this distribution? So this is represented by that, and I'm just saying, well, you know what? This xj falls there. Therefore, the probability that it belongs to that distribution is high. But what I do here is this is equivalent to saying that I'm multiplying all the values. So px1 times px2 dot, 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 px n. And this is just a shorthand notation for that one. This is a multiplication. Any questions?
No.
No question. Yeah, go ahead. Someone was going to ask a question. No? Susanna, no question?
No, I'm good.
Okay, all right. So just to remind you this, if it's something like this, I equal 1, n of I, that's the sum, right? So that's just 1 plus 2 plus 3 plus dot, 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 plus n. If I do, oh, sorry, not that one. If I do this symbol, I equal 1 to n, I, that's 1 times 2 times, let me just do, times 3, dot, 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 times n. Okay, so that's just what that means. So that's basically all the intuition, and now we are ready to summarize the algorithm. Okay, so in summary, the anomaly detection algorithm is as follows, okay? So first, number one, identify the features. So that's, you know, source port, destination port, and so on. So that's F1, F2, all the way, dot, 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 to Fn, right? Simple. Number two, calculate the mean of each feature, J, and the variance of each feature, J. So, you know, the calculate mu J and variance sigma J square for each feature, J. All right. To do that, we have the equations mu J equals 1 divided by m, the sum from I equal 1 to m of xj, right? All right, so all the values for that feature j gives you the mean j. Does that make sense? Does that make sense, guys?
Yeah.
All right, for the next feature j, we calculate the variance, and that's going to be, given all the values there, we take the sum from I equal 1 to m of the difference between that xj, or for that feature, that x value j, minus the mean of that feature j squared. Okay, so you calculate those. Then, number 3, given a new example, now this would be, so now you built the anomaly detection algorithm, it exists out there. Now you get a new sample, you know, maybe it's an attack or something, you know, on the network. So you get a new example, X, right? And you compute PX, which, remember, it's the interpretation is the probability that that sample belongs to that normal distribution. If it doesn't belong to the distribution, it is a, what is it? An anomaly, right, guys? Are you following me?
Yeah.
Okay, and the definition of PX is then a multiplication symbol from j equal 1, right, for all the features n, the probability of xj, right? So the probability that that xj belongs to that mean j and that variance j. Okay, and that is also rewritten as, just going to change the term. So this, because this is the equation that we defined before, this one, right? So this equation, I'm replacing it in there. So this is literally what you guys would have to have there in your code now. So J1 to n of 1 2 pi square root standard deviation j exponential of minus xj minus mu j divided by 2 variance, oops, no, j squared j. And that's just basically plugging in that formula in. And that's really how you do it, right? So remember, this is the multiplication, so you do it for every feature. Okay? And then from that, you have now a px value, so you're going to have a px value. And so now anomaly, if p of x for that sample is less than epsilon. And that's it.
All right.
You see that?
Yeah.
Okay, good. So now to summarize, let me just say, for instance, so remember, you have something like this made up of x1, x2, you had some data. And then in the data, you have, your normal distribution. So now if it falls over here, it's an anomaly. But now you have an algorithm that actually can do that for you. Okay, that it can do that for you. So for instance, if let's say that the probability, so epsilon, so let's say epsilon, so one example here. So epsilon is 0.02. That's the value you computed. And then you calculate for px and you get a value of 0.0021, right? That's your value. So that you computed. So now that's equivalent to, you have that, right? And now you need to place x in there. So what do you end up with? Px in this case is what in relation to epsilon? Is it less than epsilon or greater than epsilon? Epsilon is 0.02. And this one is 0.0021. So what is px? Is it greater or less than?
Listen.
Less than, right? And so it's less than epsilon. If we look at the algorithm here, it says something that is less than epsilon is what? Anomaly.
Anomaly.
Which basically means in terms of this, right, that it fell like there, right? Do you see that? So that's, you get that value, the probability is there, and basically intuitively you can interpret this as saying, well, this sample has a probability of only 0.0021 of being part of that distribution. Therefore, it is not part of that distribution, and instead it is an anomaly. Does that make sense?
Yeah.
Okay, and that's it. So that's an anomaly detection algorithm. Pretty simple, right?
Okay. Yeah.
Yeah, I mean, it's basically just statistics, what you learn in your stats class, just applying it to your network. And so anyway, so that concludes my discussion on anomaly detection systems. If you have any questions about it, please let me know. And then now you have a choice to make for basically tonight, talk with your teammate and let me know if you would like to implement this algorithm, an anomaly detection system, collecting some data. Remember, basically you're just collecting normal data. And then, so basically either select this for your project or select, like Trevor asked at the beginning of the class, enhancing a VPN and just making it more interesting. So you have to choose one of the two topics and then just work on those, okay?
All right.
Yeah, remember that this topic will be on the exam still. So on the final exam, I will ask questions about anomaly detection, but I'm not going to require you to do a lab. Instead, this Thursday, we're just going to go back to the VPN lab and try to wrap that up.
Okay.
All right, so are there any questions before I sign off here?
No, we're good.
No.
Everyone's good?
Mm-hmm.
Yeah, I think that's cool.
Good? Okay, so I'm gonna sign off then, and I'm going to be.
Not related to
Oh, yeah,
454, but
Yes.
is there a time that we can speak for our 490 project?
Yes. How about Thursday between 2 and 5?
I get off work at 5, so I can probably sign on around there. I'll talk to the other two.
I have a class, as you know, at 6, right? With you.
Yeah.
Oh, something between 5 and 6. Just we can meet there.
Okay.
Make sense?
Yep. Thank you.
All right. Thank you. Anything else?
No.
All right, guys. Then I'm going to sign off here and submit the video, post the video, and then I will see you guys on Thursday.
Okay.
Okay, great.
All right. See you then.
Yeah.